Hello everyone, welcome to the Chemistry channel. So today we're going to be beginning our sixth lecture on atomic structure, and we're going to be continuing our discussion by discussing the shapes associated with the different atomic orbitals. We're only going to be talking about the s, p, and d orbitals because the f orbitals are very hard to visualize. So we're only going to be talking about the s, p, and d, and that's usually what most general chemistry courses focus on. So with that, let us begin. So let's first, before we get into the shapes, remind ourselves of what orbitals are. So what is an orbital? An orbital is a region in which an electron can exist. And recall from one of our last videos that orbitals can be described by both their shape and energy. So in the last video we talked a lot about their energy, and in this video we're going to be talking a lot about their shape. So let's begin with the s orbital. So let's remind ourselves what the s orbital is. So the s orbital, or the s subshell, is the lowest energy orbital of an electron shell. So it's the lowest energy orbital present within a specific electron shell. So the s orbital has an L value equal to 0, as you may remember. And the s orbital is also spherically symmetric. So what does that mean? So spherically symmetric means that the probability density of electrons at the same distance from the nucleus has the same energy, has the same probability density as another location at the same distance from the nucleus. So a spherically symmetric means that the probability density of electrons at a particular distance from the nucleus has the same probability density as another location at the same distance from the nucleus. So in other words, if let's say your electron is here in the x direction, the probability density in this area of the graph here would be the same as this area in the graph here, because this area is at the same distance from the nucleus as this area. So it's basically saying that areas with that are the same distance away from the nucleus have the same probability density, and that's because it is a sphere. So this graph you may remember from one of the last videos, and this graph basically shows you that the s orbital has a spherical shape, and you may remember this from one of my last videos. Although the s orbital has a spherical shape, what happens when the n value, or the principal quantum number, increases for the s orbital? So the only way that we can describe this is through radial probability density. So we can describe how n affects an orbital by looking at the radial probability density. And recall that n refers to the principal quantum number, which basically states the energy of your particular electron shell. So what is the radial probability density? The radial probability density shows the probability of an electron existing at a certain distance from the nucleus. So these two graphs here show you what a radial probability density function looks like. So let's first look at this graph right here on the left. So this graph corresponds to a 1s orbital. So here on the y-axis here we have probability. So as we go from bottom to the top, the probability increases. And at the bottom here at the x-axis, we have the distance from the nucleus. So as we go from left to right, the distance from the nucleus increases. So what does this green line show you here? This green line shows you the probability of an electron existing at a certain distance from the nucleus. So as we can see here, the curve here has a peak. And this peak right here corresponds to the most probable distance. And I'll just use a shorthand notation for this by calling it XMP. So this is the most probable distance from the nucleus that a 1s orbital can exist. So as you can see here, the most probable distance associated with the 1s orbital is very, very, very close to the nucleus. So the most probable distance for a 1s orbital is very close to the nucleus. So now let's move on to the 2s orbital. So here we again have in the y-axis increasing probability going from bottom to top, and then increasing distance from the nucleus from left to right. So let's first look at the two peaks. So we have one peak here and one peak here. This tallest peak now, right here, basically shows you that the probability of finding an electron in the 2s orbital is at a further distance away from the nucleus is much greater than it is to find one closer to the nucleus. So this is now the most probable location. So this is X most probable. So as you can see here, as we increase the value from n equals 1 to n equals 2, XMP increases. However, there's another thing that you should note here, and it's this little area right here where the green line intersects with the x-axis. This is called a node. And as you can see here at the node, probability is equal to 0. So the electron has a probability equal to 0. So the probability of an electron being at this particular location away from the nucleus is equal to 0. So let's define what the node is down here. So a node is an area where the probability, so this means probability, is equal to 0. So it's an area where the probability is equal to 0. So it's an area where an electron cannot exist, and that is the node here. So as a general rule, as the value of n increases, the number of nodes increase. So this is a radial node, so I'll put that on here. So this is a radial node. So the number of nodes increases and the number of peaks increase. So if we look here, we can clearly see how when we go from the 1s orbital to the 2s orbital, we can see here that the number of peaks increase from 1 to 2, and the number of nodes increase from 0 to 1. So there's actually a general rule that you can use in order to find the number of peaks in an s orbital and the total number of radial nodes. So the number of peaks in an ns orbital is always equal to n. So for example, if you have a 3s orbital, you'll have 3 peaks. If you have a 4s orbital, you'll have 4 peaks. If you have a 5s orbital, you'll have 5 peaks. So the number of peaks in an ns orbital is equal to n. The total number of radial nodes in a particular orbital, so this equation that I'm going to give you applies to any L value. So this is L value. So this equation will apply to any L value. So this will work for S, P, D, F, etc. orbitals. So the total number of radial nodes in a particular subshell or orbital is equal to n minus 1 minus L. So this is equal to the total number of radial nodes in a particular orbital. So where n is equal to the principal quantum number and L is equal to the angular quantum number. And we're going to be using this later on. So here I once again am reiterating the same stuff that I said, but in written form. So as the principal quantum number increases, the number of peaks increases, the number of nodes increases, the probability density of electrons existing further away from the nucleus also increases. And if we go back to our graphs, we can see how this happens, because as we go from the 1s orbital to the 2s orbital, we see how the probability basically does a right shift. So more electrons are existing at further distances from the nuclei. So that's why as n increases, the probability density increases further out from the nucleus as well. And also we saw that as n increases, x most probable increases as well. So these generalizations here are something that you will want to know. So as you may have seen in your textbooks or in your lecture, we can symbolize the s-orbitals like these spheres. So these correspond to the different s-orbitals at the different energy levels. And as you see here, as the principal quantum number increases for each s-orbital, the s-orbital gets larger and larger and larger. So 1s will be the smallest, and then 3s here in this case will be the biggest. And these can correspond to their radial probability functions. So here we see in this graph that most of the electron density will be closer to the nucleus. In this graph we see that more electron density will be further away from the nucleus, and then the same will be for the 3s. So as n increases, electron density away from the nucleus increases, and the size of the orbital increases. So once again, this is just reiterating those points as well. So that is the s-orbitals. So now we're going to talk about the p-orbitals, or the p subshell. So you may recall from my last video that the p subshell has 3 different orbitals. And the L value for these orbitals is equal to 1. And this is, remember, the angular quantum number. So if we were to label a orbital diagram of a p subshell, you would have a -1 orbital, a 0 orbital, and a +1 orbital. So these would be your magnetic quantum numbers, talking about the orientation of the orbital. Okay, so there are 3 p orbitals that you should know, and these are the px, py, and pz orbitals. So all the p orbitals have this like dumbbell shape to it. And the dumbbell shape, the dumbbell type orbital will be aligned on a particular axis. So as you can see here, the px orbital has a dumbbell aligned on the x-axis. And if we look at the py orbital is aligned on the y-axis, and the pz orbital is aligned on the z-axis. However, I also have here some positive and negative signs showing you where the wave function is positive and negative. And these positive and negatives should make sense to you, because if you look at the positive end here, this positive end of the wave function is in the area where x is increasing. So this is the positive x region, so that wave function will be positive. And in this in the negative region, we can see here that this part of the dumbbell is in the negative region of the x-axis, so that's why this is negative. So you can sort of follow this for each of these orbitals. So for example, the z orbital, you could see here that the positive end of this p orbital is in the positive region of the z-axis, which is why it has a positive sign, and the bottom portion here is in the negative portion of the z-axis, so it has a negative sign. So these are the 3 p orbitals that you should know. So the number of nodes for a p orbital depends on the value of n. And that is because, remember, that the number of radial nodes is equal to n minus L minus 1. So as your value of n increases, the number of radial nodes increases as well. So let's do two examples here. So here we have 2px, so a 2px orbital. So this 2 is telling us that n is equal to 2, so we'll put 2 right here. It's a p orbital, so L is equal to 1, so minus 1. And then we have a minus 1, which means for a 2px orbital we have 0 radial nodes. So let's do the 3pz one. So we have an energy level, or a principal quantum number, equal to 3. And then our L value is equal to 1, so minus 1, and then minus 1. And then you get 1 radial node. So the amount of radial nodes you get, or the number of nodes you get, depends on the principal quantum number. So the last subshell that we're going to talk about is the d subshell. And the d subshell has 5 orbitals. And the reason why it has 5 is because it has an L value equal to 2. And when you label the orbitals on an orbital diagram, you would label them like -1, -2, 0, 1, 2. So these different numbers here, remember, correspond to the magnetic quantum number, or their orientation in space. So the d orbitals are a little bit more complicated than the p and s orbitals, but you still do need to know them. And their names actually tell you how they look as well. So for example, let's look at the first orbital here. The first d orbital is a dxz orbital. So what does this mean? Well, a dxz orbital means that your d orbital is aligned on the xz axis. So here in purple, I outlined for you what the xz axis is. So the xz axis is basically this square that covers both the z-axis and the x-axis. So therefore, the dxz orbital lies on the xz plane. So this plane is like this paper that I drew for you, this purple box. So as you can see here, the dxz orbital lies on the xz plane. And once again, we have our negatives and positives. So the negatives will be in areas where, so negatives for the dxz orbital will be in areas where x is decreasing and z is increasing, or where x is increasing and z is decreasing, because you can think of it as when you multiply x and z together, if you multiply a positive and negative, or a negative and a positive, you'll get a negative number. And your positives correlate to where x increases and z increases, or where x decreases and z decreases. So this general way in which you can determine whether a side is positive or negative can be applied to the other orbitals as well. So next, let's look at the dxy orbital. So here we have the xy plane, and the xy plane consists of both the x and y axis together. And you can see here that the dxy orbital lies along the xy plane. So you use the same rules that we use for the dxz orbital in order to determine whether a side is positive or negative. So if it's negative, x decreases and y decreases. So x increases and y decreases. For a positive, you can have x increasing and y increasing, or x decreasing and y decreasing. And also for negative, you can have x decreasing and y increasing. So that's how you label that as well. And the last one here that you can use this rule for is the dyz orbital. So the dyz orbital is aligned on the yz plane. So as you can see here, the yz plane consists of both the z and y axis, and you label this the exact same way as you did for these two orbitals. So if you have a positive end, it will be when, sorry about that, let's fix that. So if you have a positive end of the orbital, it will be when y and z both increase, or when y and z both decrease. And if you have a negative end, it will be when y increases and z decreases, or when y decreases and z increases. And once again, you can think of this as multiplying a positive and a negative together, or a negative and a negative, or a positive and positive. So that's how you can think of the that's how you can think of this stuff in order to determine the positive and negative signs. So the last two are the dz squared and the dx squared minus y squared. So once again, you can label the positive and negatives here. So the in order to find the positive, you know that whenever you square a number, you always get a positive value. So even if you have, like, say, -2 squared, that would equal 4. Or if you had 2 squared, that would equal 4. So that's why the x region, which corresponds to the x squared region, corresponds to both positive values, because your x squared is positive. Therefore, both ends will be positive, the negative and the positive region. However, the y region, or the y-axis, is always negative, and that's because you have a negative sign in front of the y squared term. So even though if you have, like, let's say -2 squared, that will equal to 4, and you have this negative sign in front of the y squared, so that you will always get a negative number for the y term. So that's why both ends are negative for the y, and that's why both ends are positive for the x, because the x squared region is positive, the term is positive, and whenever you square a number, you get a positive number, so both ends are positive. And the y region is all negative, because whenever you square a number, you get a positive, and since the term itself is negative, both regions are negative. So the dz squared has positive ends on both the bottom and the top of the dumbbell, and a negative ring. So this one is actually probably, I find, the easiest to remember, because it's the most distinctive out of these orbitals. So that is all the d-orbitals. And of course, the number of radial nodes depends on the value of n. So you would once again use the n minus l minus 1 equation. Okay, guys and girls, this is the practice questions part of the lecture. So I would encourage you to try these practice questions for yourself, see what you get. And if and check back with me in a little bit once you're done. Okay, so I hope you did these problems yourself. So in the first question, I ask you how many radial nodes are in the 4s, 4p, and 5d orbitals. So in order to answer this question, you have to use the n minus l minus 1 equation. So let's do a little chart here. So we have the 4s, 4p, and 5d. And let's make that a little straighter. So let's make that a little straighter. So we'll put the n value here and the l value here. So the n value for the 4s is 4, and the l value, or the angular quantum number associated with s, is 0. So therefore, the number of angular nodes radial nodes that we would get is equal to 4 minus 0 minus 1, which would be equal to 3 radial nodes for the 4s orbital. So for the 4p orbital, our n value, or principal quantum number, is equal to 4. Our l value is equal to 1. So therefore, we get 4 minus 1 minus 1, which is equal to 2 radial nodes for the 4p orbital. And then the last one is the 5d orbital. So our n value is equal to 5, and d has a l value equal to 2. So therefore, using our equation, we have 5 minus 2 minus 1, which is equal to 2 radial nodes as well. And that is the answer for the first question. So I hope you guys got this second question, because I didn't really go over it in the lecture, but however, I'm going to go over it now. So how many angular nodes are in the 4s orbital and the 4p orbital? So angular nodes refer to the actual shapes of the orbitals themselves. So let's just quickly draw both the 4s and a 4p orbital. So here's the x, y, and z direction, and here's our 4s orbital. So it's like this sphere. So this is a sphere, and it's the 4s orbital. And now let's draw the 4p orbital. So I'm just going to choose an arbitrary p orbital. So I'll just use the pz orbital. So x, y, z, and then we have our pz orbital. Okay. All right, so here's our 4p orbital, and here's our 4s orbital. So let's first remember what a node is. A node, remember, is a region where an electron does not exist. So it's an area where the probability is equal to 0. So in order to find the number of angular nodes, all you have to do is use this equation. So the number of angular nodes is equal to L. So L being the angular quantum number. So for example, if you look at our picture here for the sphere, you'll see here that there is no nodes present, no angular nodes present. And we can see that from the equation here. So the number of angular nodes is equal to L, and since L equals 0, there's 0 angular nodes in a 4s. So let's look at the 4p more closely. So I'm going to draw it a little bigger. So I'm going to draw the 4p like this. So why am I drawing the 4p orbital like this? Well, I'm drawing it like this because I'm not saying I don't have any radial probability in here. In other words, it's basically like two pure spheres. So as you can see here, there is a region in which no electrons exist. And it's on this plane here made by the x and y axis. And this is referred to as the nodal plane. And the nodal plane basically serves to separate the two different sides of the wave function. So here on the top of the nodal plane we have the positive region, and on the negative part of the orbital we have the negative region. And in between that is a nodal plane. And on the nodal plane no electrons exist. And as you can see here, if you even look in your textbook pictures and on this picture, you'll see here that there's sort of like this break in between the positive and negative regions. And this break corresponds to a probability of 0. And this probability of 0 means that no electrons exist in this region. And so this region is called the nodal plane, and this is the node right here. So, in other words, in order to find the number of angular nodes present within a particular orbital, all you use is number of angular nodes is equal to L. So for example, for a d orbital, the number of angular nodes would be equal to 2. In a p orbital, the number of angular nodes would be equal to 1. And in a s orbital, the number of angular nodes would be equal to 0. So with that, that concludes our discussion on the shapes of orbitals. I hope I helped you understand this material a little better. And in the next video, we're going to be talking about the multi-electron atom. So we're going to see how multiple electrons affect the energies of the particular orbitals. And then after that, we're finally going to get into electron configurations. So we're coming to a conclusion with atomic structure, and after that we'll be able to understand chemistry much better. So with that, I thank you all for watching, and I hope to see you next time. See you around, everyone.